the language of the universe.
But I don't understand it.
Hello, everybody, and welcome back to the Math and Physics Podcast. I'm your host, Parker.
And I'm Ray, and we welcome you back to episode number 58, where today, contrary to episode number 2, for those who remember, named Higher Dimensions, today we are going to be talking about lower dimensions. Let's talk about the 1, 2, and 3.
That's
Because
right.
in episode 2, we started, I believe, from 4. So,
Well, I think we talked about, we compared what higher physical dimensions would be in comparison to 3 dimensions. And I don't actually remember. This is literally a year ago. Pretty much.
It was
pretty much
almost a year ago. Wow, yeah, that's true, eh?
Yeah. And
That's
so technically this was our very first episode because the first episode that we put out was pretty much just an introduction to it was so awkward. I listened to it not the other day, 2 months ago. I listened to it and it's so awkward.
The very first episode? Oh my. Yo,
Yeah.
it's terrible because so there's first of all so much lag, and I didn't even have a mic at the time. I think I was using the Apple earbuds microphone. So it was it was all the way back there, and there was so much lag. It was just a really awkward episode, but I guess that was our first one, so it's still monumental.
It is what it is.
But I think our second episode, as you said, was really our first episode where we actually got into some physics. And in that episode, we spoke about higher dimensions. And actually, I think it's still one of our top downloaded episodes. So that's really cool because it's also one of our oldest.
I think it's the second most downloaded after the
really?
first episode.
Wow, that's nice. That's cool.
Yeah, our first episode almost has 11,000 downloads.
Because it's the trailer, right?
Yeah, it's the trailer on Spotify. And
so I guess when people try to discover us, they're like, oh, let me just try to discover, and boom, just download the first episode.
Yeah.
Yeah.
But here we are. This is not technically a part 2 to the higher dimensions. It's just kind of we did higher, now we're going to do lower. There's a lot of fun stuff to cover, especially because as 3-dimensional creatures, we can actually kind of look down on these dimensions. And I think it's more interesting, instead of looking down on a 2-dimensional world and it's oh look, they're flat, whatever. It's more fun to put yourself into the body, the perspective of these lower dimensional creatures, and kind of imagine what it's actually like, which we're of course going to talk about.
Also, the blatant advantage of lower dimensions is that we can visualize it, right? Because I think one of the biggest restrictions with higher dimensions is that you just, especially, even 4, anything after 4 and including 4, you can't really visualize. You're all just, making abstract assumptions in your head. Nothing that's really, that you're really thinking of has concrete visualizations, right? But when you're talking about lower dimensions, all of that now makes sense. We can visualize a line, we can visualize a square, we can visualize a cube. All of these things exist, and we can see them, we can talk about them. So even though the physics and the math that we're going to be talking about is very similar, but in contrast, that's what we're going to be discussing, to higher dimensions, it's a very interesting, niche, because these are the ones that we can actually actively visualize and, conceptualize. Truly understand, basically. Yeah.
And the best part about dimensions in general is the analogies that you can draw. Because if you understand the first dimension, the second dimension very well, you can draw a lot of analogies into the third dimension. And then from there, not visually, but more mathematically, you can pretty much just do everything, just translate everything and just add a dimension and everything follows. For example, dot products and things like that. They still represent, how it's a measure of how aligned 2 vectors are. So if 2 vectors are perpendicular to each other, the dot product is going to be 0. But if they're aligned, then it's whatever. What I was trying to say is that we've done the higher dimensions. Now let's look at the lower dimensions and see what information can we extract from these lower dimensions, and what can we say with that information about 3 dimensions or beyond that. So now before we actually get into the podcast.
Oh yeah, go for it. No, sorry, yeah. So I was just talking about on the Trevor Bassett episode, we were actually very briefly talking about these higher dimensions and the ways to, like, how can we, if we can, ever visualize these higher dimensions. And as you were just saying, how it's all embedded in mathematics. So, you know, like I totally agree with that. And in lower dimensions, on contrast, even though it is embedded in mathematics, and we can apply everything that we see, or at least most of what we see in lower dimensions to n dimensions almost. Like, it's a very nice, as you said, like you can apply like an analogy to lower dimensions. You can understand it in a different way that we understand the same thing in 5, because we see something in 2 and we apply it in 5 or 4 or whatever. So we're seeing it, we're visualizing it, we're first thinking about it in a lower dimensional sense, and then we're always usually generalizing it to higher dimensions. So that's usually the process. So that's why lower dimensions are so important, right? Because that's where you usually start from. You start from that lower dimension and then generalize.
That's right. And also, as Trevor said, when you go from 1 dimension to 2 dimensions, there's a very big gap between those two, because you go from having 2 directions of motion, just forward or backwards, to having an infinite amount. Because in 2 dimensions, you can go any direction you want. There's no like quantization, right? And then beyond there, it gets easier because you go from having, an infinite amount of directions that you can move into, and then 3 dimensions, you just have more infinite directions.
In 2 dimensions, though, how is it? Isn't it just 4 directions? Because it's like back, like forward, backward, left, right? Like, I don't, like, what are the other, how are there infinite?
No, I'm talking about like directions. Like, for example, let's say the direction is along a unit vector that is pointing like with an angle from
so you're like basically
x-axis.
saying it's...
Yeah, so I'm saying
it's all about like circular. Walk, so it's like they're infinite potential points, basically.
Like since an angle is like a real number, right? You can point in any angle between 0 and 2 pi and walk in that direction. And there aren't, right, like any angle you pick, you can just divide it in 2 and go in that direction and divide it. Like there's no limit to the amount of directions you can walk in.
Oh, that's what okay, sorry. I thought you were talking about like the fundamental, because like if you're talking about like basis vectors, for example, they're only 2. No. Right? They're only 2. Yeah. So that would describe 4 directions of motion. But like I totally understand what you mean. Like because they're infinite angles. I mean, because they're infinite angles between 0 and 2 pi, you can walk in potentially infinite directions. Yeah, so that is a fun fact about the 1 to 2 switch, right? That's a big switch. Yeah.
So now, quick news here. I'm going to make this nice and quick.
That's it.
500 subscribers on YouTube.
Nice.
Thank you. Nice. 500 subscribers. Today, actually, this morning, it's Saturday today, we hit 7,500 followers on Spotify. So dope. 3/4 of the way to 10K.
Dope. Nice.
Quick reminder, make sure to follow us on Spotify and Apple and subscribe on YouTube. Other than that, we are still above 100K. The number doesn't go down.
Hey.
It's just not possible. And
then people retract their download. But that's not a possibility.
No. But yeah, Ray,
going into the segue for the comment of the week. This is not actually a comment. This is an email that was sent to us from Aljo Benedicto. So thank you, Aljo. I'm just going to kind of briefly summarize it because it is quite a long email. But basically, he's a 17-year-old student. Didn't mention from where, but I guess he's a 17-year-old student, right? He loved medical science, but because of our podcast, he, I guess, started liking physics a lot more than medical science and started just not wanting to learn medical science. Hence the change to math and physics. So basically, like, his idea is, I just want to say this podcast is the reason why I fell in love with physics once more. You guys have turned me, a 17-year-old who's in medical science, from disliking the subject to loving math and physics. So that's basically the idea of the email. So thank you, Aljo, for that wonderful email. Not comment, but still counts. So let's get into the episode, right? With lower dimensions. So let's start with the lowest of dimensions, 0. The 0th dimension, right? So many people always kind of disregard the 0th dimension because you're like, well, there's nothing really there. But is that really true?
And there's also not much to say about it.
There is not much to say about it, but there is something to say about it, and I want to mention whatever we can say about it. Because the interesting thing about 0 dimensions is that there are realistic 0-dimensional objects in our universe. And we call them singularities, right? When black hole singularities, so those are commonly known as like your gravitational singularities, are, those points in space-time that are infinitely dense and all those crazy things. And that, well, is a point. So it technically has no dimensions, right? Because it's simply a point in space that doesn't represent any direction. So, I guess before we get into the 0th dimension, we can just talk about what a dimension is. I think we did get into this in like a higher dimension episode, but we can definitely like recap, right? Because a dimension is a way of thinking as a direction of travel. So if in a point, there's no direction that you can travel, so you have 0 dimensions. On a line, there's one direction that you can travel. It's back and forth. That's basically one direction, right? Technically, like you can just walk in front and walk backwards, but collectively, that's one direction that you're traveling in. Hence the name one dimension. So the dimension term basically simply stems from, well, how many directions can I travel in? So that's why the 0-dimensional object is pretty cool, because you can't go anywhere. There's 0 directions you can travel.
Just to not confuse the people that are listening and are asking, hey, didn't you just say that there were infinite directions? What we're actually talking about in this case is that I don't know how much we can actually talk about linear algebra,
Yeah, no, but I feel it's important. I feel it's important for sure. We can get into it a little bit.
In two, for example, in 2 dimensions, we say there's like 2 directions of travel, quote unquote, because you can go you can basically reach any point on your surface or your space with any combination of 2 directions, as long as it's not in the same direction, right? Mm-hmm. So if, for example, you have back and forth and left and right, you can reach anywhere in your space just by combining movements in the back and forth and the left and right. And then if you were to be in 3 dimensions, then you would need another direction, right? Mm-hmm. Up and down to reach every single point.
And these directions are fundamentally, in a way, like we can think about it, orthogonal to each other. So this is a little bit of a linear algebra term, but basically the idea behind, right? It is a linear algebra term. Right?
No, yeah, it is. It's just they don't actually have to be orthogonal.
No. But I'm saying the directions, right, that define, because in a 3D space or in a 2D space, we have 2 basis vectors. In a 3D space, we have 3 basis vectors.
Yeah, but they don't have to be orthogonal. So I'm saying the base vectors that make up that point, right? That you said it's some combination of front and back and left and right. So those 3 vectors or 2 vectors that make up that point, are all orthogonal to each other. No, they don't have to be, actually. Just think about change of basis, right?
I guess, yeah. Okay, okay.
You can still have 2.
Yes, you can.
You can still have a set of bases, like 2 basis vectors in R2, which is just the 2 dimensions, let's say, and they don't have to be orthogonal. They just have to be linearly independent from each other, meaning that, okay, I guess saying that the definition of linear independence, it doesn't really matter in this case for like an audio experience, but as long as they don't point in the same direction, then they're linearly independent in 2 dimensions. And so just think about restricting yourself to combinations of these directions, right? So if I want to go in a diagonal direction, first I move along my first direction, until I get like far enough, and then I turn in the other direction, and then I follow that direction. Yeah.
Yeah, but I was just thinking about, yeah, you're right that they don't actually have to be orthogonal, but if they are orthogonal, they cover the whole space, right? That's the advantage. So if they're not orthogonal, they simply don't cover the whole space. So like in 2D, for example, with two vectors that are not orthogonal to each other, you won't be able to reach the whole plane. But with, I mean, the whole 2D space, right? You won't be able to reach any point in R2.
No, you totally would.
With a non-orthogonal basis?
Yeah, like what I was literally just saying, right? As long as they're not pointing in the same direction, they don't have to be orthogonal.
Sorry. Small technical difficulty here. Parker, you good?
Yep.
Sorry, I didn't kind of hear. I think you kind of cut out. You were saying something about orthogonality.
Okay. So
not being orthogonal.
Yeah, you were saying that if the basis vectors aren't orthogonal, then it doesn't cover the entire space, but that's just not true, right? As long as they're not linearly dependent, then you can go anywhere, right? But they don't have to be orthogonal. That's just a special case of non-linear independence.
Mm-hmm. Because I was thinking if they're not, because I was thinking more linear dependence. Because then I'm thinking like, what if two vectors are pointing in the same direction? Like you're not going to be able to, span the whole plane in this case. So anyways, this is a lot of tangential talk here, like on the side. But basically, the idea is that given the number of dimensions, so for example, in a two-dimensional space, given two vectors or two directions that are not dependent on each other, so as long as those directions are they do not influence each other, we can represent any potential point on this two-dimensional plane with combinations of these two vectors, right? And the advantage of this in linear algebra, for example, right, is that you can make up any two vectors, and any two vectors, obviously, that they're not linearly dependent, can be used to model any point on the surface or on the plane. So this can be a really useful tool, like, if you've been given certain directions, given certain vectors to use. So it can definitely, be useful in not only lower, but also higher dimensions. And we're going to get into that.
But here's an actual better way to understand dimensions, is that to represent a point in a dimension, right? The amount of information that you need is the dimension that you're in, essentially. If you're in one dimension, you just need one piece of information. And if we just model like the real number line and we give every point a number, then all you need is one number and you say, here I am, right there. If you're in two dimensions, you need two separate numbers, right? And this has to do with the directions, right? You set your axes. Usually it's easiest to make them perpendicular to each other, and then you just say, I am this far along the x and this far along the y, and then you can basically place any point in two dimensions. And then the same thing goes for 3 dimensions. You need 3 pieces of information and all that stuff. And what's even more interesting is that you don't even have to describe your point in like rectangular coordinates. For example, you can do it in polar coordinates, where in 2 dimensions you need a length and an angle. And that's still 2 pieces of information, and you can actually still determine like the position of any point. Yep. When you get to 3 dimensions, you still need 3 pieces of information, but there are different ways of doing that. You can do rectangular, which I described earlier. You can also do spherical, where you need a length, basically a distance from the origin, and then 2 angles. Or you can do cylindrical, where you need a distance from the z-axis, an angle in the xy plane, and then a z height. It's,
Yeah, so all of this would be a lot easier like with visual aids, which unfortunately we do not have right now. But I think the 2-dimensional case made a lot of sense with polar angles, because you're just imagining some distance and you're imagining some angle from the x-axis, right? We always do it from the positive x-axis. And then in 3 dimensions, you can really generalize it to some interesting stuff, right? Because then you have that third dimension. So in 3 dimensions, much like, for example, so the reason it's also called spherical is because it is most used and most helpful when you want to describe, well, a sphere. So take the Earth, for example, right? If we wish to describe the Earth or any point on the Earth, like let's say the center of the Earth is the origin in this 3-dimensional world, and we wanted to represent any singular one point on the Earth, anywhere, how would we do it? Well, the first dimension, right, the distance from the center will simply be, well, the distance from the center, right? The second dimension will be your latitude. We already know our latitudes and longitudes on the Earth. And our third dimension will be our longitude, right? So we have some direction that tells us, well, how far are we from the prime meridian? So in terms of angles, right, which is Greenwich. So in terms of angles, how far are we from the prime meridian? That will tell us one of our dimensions. The other dimension will tell us, well, how far are we from the equator, right? Are we up? Are we down? So using these 3 numbers, are we up? Are we down? That's a pretty poor way to describe it, but you know what I mean. But using these 3 variables, we are able to describe any point on the Earth. And remember, the spherical coordinates, again, are most useful when we're using a sphere. So it's so simple to describe any point using latitude and longitude because our Earth is a sphere. If our Earth was like a rectangle or a square, which I know it's not possible, but hypothetical, it would be a lot harder to represent it in terms of spherical coordinates, and we would use, well, rectangular coordinates, right?
All right.
So there are other options.
Talk about.
Yeah.
We went off from like 0 dimensions and then talked about 3 dimensions for no reason.
Yeah, we really
go
went
up
off
to 1 dimension now. So now, in 1 dimension, I actually mentioned this earlier, we can represent this physical dimension with just the real number line. And of course, we, just because it's convenient, we put the origin in the middle, and then if you go to the right, you go in the positive direction, and the left is the negative direction. And so all you need to describe a position is a single number. And as I said earlier, that's what makes 1 dimension one-dimensional, right? So now let's talk about a creature that is living in 1 dimension, okay? So if you were to be like a thing, like an object in 1 dimension, you would essentially be a string of atoms, right? But like flat atoms, because it's kind of, it doesn't even make sense to talk about atoms because atoms are 3-dimensional.
Yeah, you can't right? conceptualize atoms in 1 dimension. No, like there would be a whole new form of life, like if that's even possible. But there would be a new biology that governs that dimension.
I didn't mean literally atoms. I just meant like it's just like a blob, but it's a line.
Okay, first of all, though, biologically speaking,
like it's a line.
Like that is simply
doesn't make sense.
Yeah, it's just an impossibility because there are certain very basic things to happen, chemically speaking.
Okay,
they're
but Ray,
required to
we're
be
just having
angled
fun
and
here.
stuff. I know. We're all hypothetical. I know. I'm just saying. If you're imagining a creature in 1 dimension, you have to think of the fact that, well, maybe that's not even possible, or maybe just bring it up. So it's a funny thing to think about.
Okay, so let's just pretend for 1 second that it just works. Okay, you just have this. Okay, and so of course. Evolution, right, would require to have like an eyeball on the front, right, to know where you're going, right? Maybe an eyeball on both sides, just so you know, like, if you move in either direction, you know what's going on, right? So what would you see as a 1-dimensional creature? What would you see? Well, actually, it would kind of be like a binary vision, right? It's either there is something in front of you or there isn't, right? I don't think there would be much like use for color, right? You know what I mean?
Color? We're talking about color, bro. This guy is gonna start walking and he's gonna see something and he's just not gonna be able to go through.
No, but do you know what I mean?
How sad is that?
If there's anything in between like him and infinity, then like it would just be blocked off. His vision
That's
would
exactly
just
what
be
I'm
blocked
saying. That's
off.
exactly
No,
what I'm saying.
exactly.
He will never be able to go through. He will never be able to go through that.
But listen, this is what I'm saying. His vision is basically binary. If there is something in front of him, then he sees like black. But if there's nothing in front of him, then he sees white, for example. This is just an example.
Okay.
But that's how vision would work, right? In one dimension.
I mean, well, yeah, if we're actually thinking about the very hypothetical question, how would we see in one dimension, then yeah, I guess you're either seeing something or you
this
aren't.
is implied, Ray.
Yeah,
this is
okay.
obviously implied that it's hypothetical.
Okay, I mean, no. Obviously, I understand that you know it's hypothetical, but I'm just making like I just need to make sure that like we have the correct framework for saying, well, this is just not a possibility. But thinking about it, yeah, well, I'm just again, as you said in the very beginning of the podcast, put yourself in that dimension, like put yourself in a creature's shoes in one dimension. If you, like, for example, think of yourself like on a line or on like a circle or something like that, like you're only going in one direction. You're only moving in that one direction. So you're right. You're either, if there's something in front of you, you either see it or you don't. Like there's either something there or there isn't.
Yeah, exactly.
There's not much more that can really happen.
That's what I mean.
It's a very
That's
sad
what I mean.
life.
There's not much more that can happen
It's a
in
very
one dimension.
sad life.
Yeah. Plus one reason to justify why this is not possible is because if you have a stomach or something, nothing would be able to get in because there's no opening, right?
Why
there's
are we
just
applying
there's you
human logic
and-
to one-dimensional beings, though? Like, I don't understand why. Maybe they
I'm
don't
just
eat.
saying.
Maybe I don't know. Like, maybe I don't know. I'm just.
Okay, sure.
That's very, very hypothetical. But
Okay.
one thing
anyways,
that we can extrapolate, though, out of this one dimension, even though it is one dimension, is the fact that there are two. Like, okay, I know this kind of contradictory because I said one dimension means one direction, but technically, like, you know, that one direction is back and forth. So technically, like, you know, like I can go forward or I can go backwards. So that's two ways of travel, right? I'm just gonna call that from now on. I'm just gonna call that direction, even though like you guys kind of know what I mean when I say direction now. So in this case, we have these two directions of travel, right? Now, what that can tell us is something that we can and we do apply to higher dimensions. Vectors, right? The concept of vectors and scalars. So, right, so vectors, right, come out from, well, we have something going in a specific direction with a certain magnitude, right? So in one dimension, the idea of a vector doesn't, or at least to me, it didn't make a lot of sense. But then as I started to think about it, like if any point on the number line like can be represented by a value. So if we're looking at x equals 5, well, the value is 5, right? So it's represented by some distance from the origin, so that's 5, and it's represented with some direction, which is forward or in the positive, right? So we have these two directions in one dimension where, again, you might think that there's no application of these vectors in one dimension. But again, like when we move to further and higher dimensions, like 2, for example, that's where we see the application of these vectors and where they differentiate from scalars, right? So scalars are another part in one dimension, right? For scalar quantities, we simply have, well, the value. We don't really have anything, no direction, nothing telling us anything about the quantity itself, just 5 or 6 or 7. That's a scalar
Well,
value.
scalars are actually vectors in one dimension.
Exactly, in one dimension, yeah. Go for it.
Yeah, so, I mean, you pretty much said it all. But what I wanted to add was basically I just want to bring in a little bit of topology here and talk about a sphere and talk about balls, right? And we're going to compare through the definition of a sphere, we're going to see what that looks like in one dimension, compare what that looks like in 2 dimensions and then 3 dimensions.
Don't you mean ball, though? Like sphere, is that not 3-dimensional? I could be wrong, but is a sphere not specifically...
I'll give you the definitions here. So a sphere is... There's a center and there's a distance, okay? You need 2 pieces of information here. It has nothing to do with dimensions here. But so you have a center and you have a distance. And the sphere is just the set of points that have that distance away from the center,
Or within
Okay?
that distance? Or
No,
is it
a
exactly
sphere.
that?
A sphere is exactly
Exactly
that
that
distance.
Okay.
And then a ball is just the set of points that have up to that distance
Oh,
away
okay.
from the center. So a ball is actually filled in and a sphere is hollow. But so let's for the rest of this episode, when I talk about a ball, we're just going to say it's centered at 0, just to be, just for ease, I guess. And we'll say that the radius is 1, the distance is 1. So I'm always going to be talking about the unit sphere, the unit ball. So in one dimension, the ball is actually I'll start with the sphere. The sphere is actually just 2 points, right? Because if you're centered at 0, how many points have exactly a distance of 1 from the origin? Well, there's the point 1 and the point minus 1. So a sphere in one dimension is literally just 2 points. Now, if we talk about the ball, it's the set of points that have up to a distance of 1 from 0. And so it's literally going to be the interval from -1 to 1. So it's going to be like the filled in interval from -1 to 1. That's what a ball looks like. And of course, you can define your ball differently. You can say it's centered at 5 and it has a radius of 100. But, it's pretty much the same thing as what I described 2 seconds ago, where it's just going to be an interval. You go one way, you go the other way, and they both have the same length distance away from the center.
And
can we move on to 2 dimensions now?
Now, just before we do that, though, I do want to talk a little bit about the concept of the ball, right? Like, why did Parker just bring up this random ball and sphere? So the interesting thing about these higher dimensions, and when we're generalizing anything, we get to this concept in math, and this is a very useful concept in math, where we say close to, close enough, when this is close to this, when x is close to p, when x is around p, or something like that. So even though that you might think, well, that's not a mathematical word whatsoever, it is the most mathematical word you'll see, because close to, even though you might not really think about, close to, how would you rigorously define that? How close? So in math, whenever we say the words close to something, we mean a distance or a ball of radius epsilon. So epsilon is just a hypothetical variable.
Wait, before you say this, what Ray is trying to get at is when you say close, essentially we mean as close as you want. Right?
Yeah, no, but I mean that's exactly
point.
What I was trying to get to. The epsilon, right?
I meant
the epsilon is just a variable.
No, but before you say, okay, epsilon and everything is contained within the ball, is like, when we say close, we just mean as close as you want. That's
okay, well, the idea of as close is as close as you want, or arbitrarily close, another word very commonly used. But basically, this epsilon variable is just any hypothetical variable that can be replaced with any number. The idea is that something should hold for anything close to this value. So for an epsilon radius, so now we're talking about only one dimension, so it's going to be 4 plus epsilon and minus epsilon. So let's say we're at 5, so like 5 minus epsilon and 5 plus epsilon. So in that distance, something should happen. That's the idea behind saying close enough, right? Because close enough is a very important set of words that we should take very seriously in math. Because again, what they represent in one dimension can then be generalized to higher ones. So before we get into 2 dimensions, I just wanted to talk about, well, what if you wanted to learn all the stuff we're talking about? What if you wanted to know more about dimensions? Wanted to learn more about how to analyze all of these vectors that we're talking about? Well, go hit up brilliant.org, where you can find us, link in the description below. And they offer a variety of courses, especially now that we're talking about dimensions. They offer a course on dimensions, actually, and various ones on linear algebra. And obviously, the essence of this entire episode is linear algebra, because that is where all of this is kind of defined
Pretty
from.
much the essence of the universe is linear
algebra. That's a very good fact. So again, they have a lot of courses on linear algebra. And again, as we've discussed in previous episodes, the Brilliant courses, basically, it's just practice till you understand the material well enough so you can do it yourself. So they have a really good method, really good way of doing it, and you can follow it in a really good way. For example, if you don't want to start at linear algebra first, you can start at basic algebra, move to single variable, move to two variables, move to multivariable, and then basically just keep on moving and advancing forward, right? So they have a lot of these offers, a lot of these opportunities, so definitely go check them out.
And to the first 200 listeners that click our link, brilliant.org/MPP, you will get 20% off of your membership.
Yeah.
So go click that link. Go learn. Go learn something. What are you doing? It's summer. Go learn something.
So that's brilliant.org/MPP, right? Did you say that?
Yeah.
I don't know if you said that.
Yeah, I did. I said it, yeah.
Okay, perfect. Perfect. We good.
Now, the first thing I want to do when we embark on this two-dimensional journey here is compare what a sphere looks like in two dimensions. It might actually seem a lot more familiar to you. So now let's think of a center for our sphere. Let's just take the origin, right? And now think about all the points that have the same distance away from that center. Well, it's just going to be a circle, right? It's if you take, for example, a rope and you tie a pencil to it and you draw anyways, that's just a way to think about it, because it just ensures that every single point you draw with your pencil has the exact same distance, and it just so happens that it looks like a circle.
A compass. Like if you've ever used a compass, for example, you'll know exactly what this is, right? A compass has like a pencil on one side and you have an origin.
Yeah.
So when you're drawing that radius, you're basically saying, okay, everything exactly at this radius is what this sphere contains. Now, I know we've been talking about sphere for 1 and 2 dimensions, but it might be confusing to some people still, because I think embedded in memory is that sphere is a 3-dimensional object. So throughout this entire episode, and you might have already guessed from when we were talking about sphere in 1 dimensions, we obviously don't mean the three-dimensional sphere, but it is the sphere is an important mathematical object. So the mathematical object sphere and the topological object sphere, topological meaning the physical, the algebraic sphere that we know, like the Earth, for example, they're two very different things. So the mathematical sphere is what Parker is talking about and what we're talking about in terms of intervals and circles and all this stuff. But the topological sphere is quite different. So just to get that idea in your head, and just so you know that,
So I actually just thought of something, and I think it'll blow everybody's mind here, and it'll kind of click in a way where you'll be like, "Damn, that's really cool." So, real quick, so we know what a sphere looks like in 2 dimensions. It's just 2 points. Right? Mm-hmm. We know what a sphere looks like. I meant 1 dimension. In 2 dimensions, a sphere is a circle, right? Because all the points along that circle have the same distance from the origin. And then in 3 dimensions, a sphere is more colloquially, right? It's like a ball, like a soccer ball, for example. Kind of this I guess the only way to describe it is as a sphere, right?
Yeah.
But it's a hollow object, looks circular. Every point has the same distance from the center, right? Now, think about this. As a 1-dimensional creature, living in 1 dimension, you see a sphere. It looks like a point, right? Because nothing has a height or a width. You're living along that length, right? You see a sphere, it just looks like a point. A point is a 0-dimensional object. Now in 2 dimensions, you are living in 2 dimensions. That means you can only see a cross, right? I feel like I can be more descriptive. Because you're living in 2 dimensions, it means your eyes are 2-dimensional, which means that what they can capture is essentially light that is a projection of the 2-dimensional world into your brain.
Maybe another way of thinking. Another way of thinking about this could be think about a plane, right? Think about you on a plane now, right? Just visualize a plane, on a 3D set, for example, or 2D, whatever. You're on a plane, and now you are that 2-dimensional object in the plane. Now, if you're on the plane and you see a plane, because now you're talking about a sphere, right? So like a sphere in 2 dimensions is a circle. So a circle, like you can kind of think about it like, again, like you're seeing something with 2 directions. Now remember, you can move in 2 directions, in these 2 main directions, right? Like this back and forth and left and right. And the circle is also defined in these 2 directions, this back and forth and left and right. So what you are seeing, I'm thinking about it now, this is not a very good example. Because I was thinking about a really good way of describing it first, but now that I'm actually saying it, I'm like, this doesn't really explain it. Because the way I'm visualizing it is I'm just picturing myself on the plane. And like if I'm seeing the same dimensional object that I am, I won't see one of its sides, right? I'll only see the side that's facing me.
Maybe this
works. The direction that's not facing me, I will never see. So even if it's however it's angled towards me, I will see one of the directions, but the other direction I will never see. I don't know if you can really picture that because I can see it in my head, but I don't know if everyone can.
But here, I'll just say what I was trying to say.
Okay.
And then,
maybe
I think people will understand, like, thinking backwards.
Okay, let's hear it.
I'll go back to the beginning. So 1-dimensional being, you see a sphere in 1 dimension, you see a point, 0-dimensional object, or it appears 0-dimensional.
Why are you talking about a sphere though? Like, shouldn't you talk about like a ball? Because we're talking about like an interval.
Just think about it.
Okay.
In 2 dimensions now, you see 1-dimensional projections, right, onto your eyes. So you look at a sphere in 2 dimensions, it looks like a line, which is a 1-dimensional sphere, okay? Now, think about a sphere in 3 dimensions. When you look at a sphere, when you look at a sphere in 3 dimensions, you don't see the 3-dimensionality of it, right? What you can actually just see is the projection of that into your brain, which is just like a circle. So you see, when you are living in a physical dimension, you see a projection down into the one lower dimension. You know. But
again, I think that a lot of that also has to do with the fact of how we see. The fact that we see,
I don't think
our
so,
brain perceives things. No, I know. I was actually reading some of these posts where people were talking about this exact thing because I was just, reading in prep for this episode. And I was seeing a lot of people are like, well, let's generalize. Because in 3 dimensions, the very common thing is, well, 3-dimensional beings see 2-dimensional objects because what is actually in our eyes is a flat screen where there's light being projected on it and our brain perceives it to be all of these objects. So we generalize the fact that 3-dimensional beings see 2-dimensional objects, the lower dimension. So 2-dimensional sees 1 and 1-dimensional sees 0. Now, I was also reading like some like theories on it, and maybe we can talk about this because I was just thinking about it. And because would there be a possibility that a 3-dimensional being can see all the 3 dimensions? I don't think that's actually a possibility.
No way.
Because how would we construct...
not naturally.
Yeah, not... But that's, again, very specific to us, is it not? Like, when we say naturally, we are the only species that are really... We are the most complex species
think about
we know,
every
right?
single living being on Earth.
Well,
it works the exact same way.
But I'm just talking about like a hypothetical being that is a 3-dimensional being that is more advanced than us or more, I don't know. I'm just thinking hypothetically speaking, would a 3-dimensional being be able to see 3 dimensions? I don't really think so. I don't really think so. I don't really think so. And I think that could be also the reason why all of this works, right? Why you're saying even in 1 and 2 dimensions, you see that one lower dimension. Because just fundamentally by the laws of physics, you are restricted to see that other direction or that other dimension because, again, you are in it almost.
Yeah,
right?
you are in it. And the reason why it's kind of hard to imagine is because we are 3-dimensional beings. So when we look down at 2-dimensional beings, we say, oh, well, I can see their entire world. So, like, I see there's a circle there. How can they not see that there's a circle there? Why do they see a line? Well, think of it like this, right? imagine if I draw a circle on a page and then I draw a square inside that circle. Okay. Now, the way you should be thinking about this is imagine in front of you right now, you have this soccer ball, and inside the soccer ball, there's a cube, right? You can't see what's inside the soccer ball because the soccer ball is in the way, right? And so when you think about that two-dimensional problem that I described 2 seconds ago, the two-dimensional beings can't see what's inside the circle because the circle itself is in the way. And so when you think about what they can actually see, you just think about like the photons that come from the side of the circle into their eyes is all they're going to be able to see. Like even if there was a chance for them to see inside the circle, I don't even know where I was going with that. I was just gonna say it's just not possible.
No, but I think I do follow you. I think I do follow you because like if you're in that, I think we're still stressing that same point that we were going for. That if you're in that situation, if you're in that dimension, that you are simply by the laws of very nature, we are physically restricted from seeing that one dimension. Or that other dimension, right? That extra dimension. Like what I'm trying to say. All of this is hypothetical, I know. But I'm just saying, right? Hypothetically, like this is basically saying that, we like this thing is restricting our view. So yeah, so it would appear as a line, like in 2 dimensions. And then moving on to 3, we see everything in 2 dimensions. So like continuing that, that one-dimensional lower. And now interesting also in 2 dimensions, something that we don't see in anything. Because so now we can also start talking about, well, what's the difference between all of these dimensions? So obviously 0 to 1 is huge. Now 2 to 1 is also quite huge. And in 2, we get an interesting thing called, or at 2 and higher really, we get this thing called the Cartesian product, where we can start to cross, so as we said, a 2-dimensional object would have 2 variables describing its location. Its whatever idea it's trying to convey, 2 variables will describe the idea. So the Cartesian product stems from this idea. Well, what if those 2 variables were not the same type? So what if both of them weren't real numbers? What if one of them was a real number and one of them was only an integer? Or one of them was a real...
Hold on.
Yeah.
You're getting ahead of yourself.
No, I mean, I'm just trying to describe like the pair of points and how you can describe them using any combination.
But I think it's important to note that the Cartesian product is an operation between 2 sets. And just like when you add 2 numbers together, you get another number. When you take the Cartesian product of 2 sets, you get another set. Mm-hmm. Okay?
Yeah.
And so, for example, if you have the set, the set containing 1 and 2, and then the same set containing 1 and 2, and you want to take the Cartesian product of those 2, we just say it's crossed, right? So we'll say the set crossed the other set. Basically, it creates another set with every combination of elements from the original set. So the Cartesian product that I just described would be the set containing 1, 1, 1, 2, and 2, 2. Because those are the only unique objects that, or technically you would have 1, like 1 twice.
Yeah.
Or 2, 1.
But 1, 1 would still be the same uniquely it would have that 1.
Yeah.
1,
there would
1,
be 2, 1 actually. There would be 2, 1. But anyways.
Oh yeah, flipped version as well. Yeah, because it's a perfect. Yeah, that's very important.
So if you take the real numbers and you take the Cartesian product with the real numbers again, then what you have is essentially ordered pairs of 2 points with the first element being a real number and the second element also being a real number. Now, we usually take R cross R, we write it as R squared. Or we don't
R2.
say squared.
No, actually, we don't say R. Yeah, we say R2.
No,
R3,
we say
R4.
I was just saying it's squared because the 2 is like in the exponential position, but we just say R2, not R squared.
And for any dimension, like even Rn, for example, hence the name, like we say Rn, like R2000. We never say R to the power of 2000, for example, right? Because it's all simply individual elements of this vector that we make up, or this ordered pair in 2 dimensions, where each of them have individual elements that are different. So the formal definition of the Cartesian product, if let's say we have A cross B, the formal definition of A cross B is the set of all points of A of all points that belong to A and all points that belong to B, as very well you said. Simply all the combination or all the permutations of all the possible points between them. Yeah, it is the permutation. Yeah, for sure. So that product, hence the Cartesian product, will get you.
No, there's one.
Will basically get you all the permutations. Is what I wanted to say.
You have to mention that sentence. Hold on. Sorry. So basically, it's important to note that when you do like A cross B, the first element of your 2 tuple essentially comes from the set A, and the second element can only come from the set B, right? You can't kind of take an element from the set A and put it in the second position.
Obviously, yeah.
But
that's the idea of, so even in R squared, or in R2, I just said R squared. In R2, for example, like each element would simply be from R, so we don't really think about it. And most of our calculations and everything we do, especially throughout high school and first year we start mixing it up. But throughout high school, we always deal with R2. We only deal with R stuff. We don't deal with these Cartesian products when we start getting into, for example, as I was mentioning before, like what if we have the real numbers cross the integers? That means the second number in this tuple of in these 2 numbers cannot be a real number. It must be an integer. It must be a whole numbered integer.
And so if you were to represent this set visually, for example, as Ray said, it's R crossed N, which is the natural numbers. The first element would be a real number. The second element can only be a natural number. And so visually, this would just look like horizontal bars that are separated by integer lengths, right? Because if you were to pick a random, and of course overlaid on top of the real number plane, right? Because any point that is in that set, R cross N, has to be along the X direction. It can be any number, but along the Y direction, you are only restricted to integer numbers.
Yeah, and XY, again, like technically if you think about it, like even using the term XY might not make... Again, XY is just a way to think about these individual representations, right? So when we say the XY plane, like the Cartesian plane, we usually, when we're talking about R2. So X can take any number, Y can take any number. So our function can be some messed up function, basically hitting any point on the XY plane. But the moment we have these interesting, like these Cartesian products that are no longer R and R, then we start to see some interesting patterns that functions must abide by. So if a function has a domain or has variables coming from this Cartesian product, we see that it's restricted to certain values, right? And as you were saying, like if we're talking about R cross N, it's restricted to those integer level steps almost. So all these functions are being restricted via this Cartesian product. So we can do some really handy things depending on the number. So for example, if we know that our variable must be an integer number, so if it's like the number of coffee you have per day, or I'm just making something up, you can't have 1.3 coffees a day, right? It's always going to be integer numbers. Well, I know you can, hypothetically, man, I'm just making something up to make you guys think of that integer number for why we would need something like a Cartesian product. Like, why can't we just use R2?
How many photons do you absorb?
Okay. Well, yeah. I mean, even that is the most perfect integer number question. Yeah, that's it. That's it.
I also wanted to talk about the fact that maybe we should make kind of a series where we kind of build from the ground up, like functions and all that stuff, because I don't know if you read this, actually. I told you to read it last year, but in the book How to Prove It by Dr. Velleman, he talks about relations and then functions. Because functions are just special cases of relations. And I don't really want to get into that right now because it is kind of a complex topic. Mm-hmm. But I think that we can talk, like in a future episode, we can talk about relations, functions, and then things like injectivity, surjectivity, bijective function, all that stuff.
Yeah, the three.
And then we can talk about functions from lower dimensions to higher dimensions to lower dimensions, parametrizations, implicit.
Because so now
sets,
actually, so like now that we're talking about all these lower dimensions, the interesting thing, and as I just now mentioned, the fact that you can also represent functions, right, in higher dimensions. Now, the interesting thing about functions is that, they might give you something in 3D, but they don't necessarily need to take in a 3D number. They can even take in a 2D number or 2D variable and spit out a 3D variable. So like if we are to do this series, we can get into some really cool things on functions that we can talk more in depth, even talking about lower dimensions. But anyways, continuing on this lower dimensional path, like we see this. What was I trying to say?
Something about
we're talking about functions, then we were talking about lower dimensions. Yeah, so I wanted to kind of touch. Okay, I guess we don't have to touch on parametrizations. I guess we can just take it in that series, right?
Sure.
I think we can just focus on that because that's again talking about how to vary. Because now we're only talking about sets. We're talking about values in R and values in N. We're talking about values in this dimension. And remember, all of these things that we're saying are basically dimensions, right? Like your R and your N are your two dimensions that we're talking about. So everything that we're saying right now is simply like, okay, you're taking something from this dimension and you're taking something from that dimension. So we're basically talking about sets, but in, more complicated mathematics, then when we actually get to functions, we start seeing, okay, well, how do these sets change relative to each other? How does X change relative to Y? How does Y change relative to X? So that's like when we start seeing these relationships, hence the term relations, and these functions where they both depend on each other. And we see some interesting stuff.
The thing is though, like have you read the book?
I've read a lot of chapters. I have not finished it. I will tell you that. I have read the functions and relations part, if I'm not mistaken.
Okay. So
that's one of the parts in the beginning of the book, is it not?
No, it's after. It's like chapter 4 or 5. Anyways,
I think I'm on.
Okay,
I'm not totally sure. I read that.
The point is that the way that they teach you functions in school is very different to what like functions actually are mathematically, or like formally, I guess you can say. And you actually, like, to everybody that's listening right now, it's probably one of my biggest recommendations, like to read, is How to Prove It by Dr. Vellman. It's quite an incredible book because you really do look at mathematics so differently afterwards. Like functions are like, yes, they're like rules, but they're so weird and different. And when you actually do like kind of bring your perspective back and you think about relations and then functions, it seems like very, very weird. I don't know.
Functions are basically like specialized relationships, so like relations. Yeah. Anyways, let's not get into functions and relations, because again, like that is definitely a very interesting topic that we can get into, but for another episode, because that has so much that we can get into. We didn't really talk too much about 3D in this episode because I think most of what, again, the advantage of actually everything that we mentioned in this episode is that we were focusing on the 1 to 2. We were focusing on 1 and 2. Now, again, said by Trevor Bassett and now clearly noticed by us, is that the 2 to 3 jump is not that crazy. When you go from 2 to 3, the ideas that you have between your sets, your Cartesian products, for example, now just add another dimension. Instead of R cross N, you have R cross N, or whatever. Like, you can have a third one. So it's very easy simply to add that other variable or that other number. And now, instead of representing any point with 2 variables, you represent it with 3. So it's a very similar idea from 2 to 3, but that 1 to 2 difference and understanding that one direction versus infinite directions and understanding, how those two tie in together. And like, you know,
Mhm.
it's a very nice it's a very nice sequence of things, you know, how they all tie in together. Like with the ball, the sphere, like how balls in 2 dimensionals represent things, and I don't know, it's very nice.
For sure. So I think we have like said pretty much a lot of things about lower
Yep.
dimensions and things like that. So
Yep.
yeah, catch us on YouTube actually, because we're gonna record very shortly a Q&A that we said we were gonna do a while ago.
We're actually gonna hop on. So obviously, for the people that watch this video, you're not gonna actually see this, but like we're gonna be hopping on Instagram live soon, hopefully, and we're gonna say hello to you guys, and then record the Q&A. So that's gonna be interesting, for sure.
All right.
And
Well, I can't
are you
see
lagging
you move
again?
right now, but
Okay, you're good. Okay, sorry.
can you hear me?
Parker.
Hello.
Parker. Yeah,
All
yeah,
right.
yeah. I can kind of see you now.
Anyways.
Okay.
I'm just gonna.
Anyways,
I'm
let's
just
do
gonna
this.
end
Yep.
it. Okay. Here we go. Here you go.
Where
So-
can you catch us? Where can they catch us though? Where they don't even know where to reach us.
Boom. So you can ask us questions. If you have any questions about like what we talked about today or anything, make sure to hit us up on Instagram at math.physics.podcast. Also, subscribe to us on YouTube, Math and Physics Podcast. Follow us on Spotify, on Apple. I don't even know where else we are. Pretty much everywhere, I think.
Yeah,
So,
we are pretty much like
So
anywhere.
yeah, make sure to follow. And we will see you guys on the next one. This has actually been officially episode number 58 of the Math and Physics Podcast. And I'm your host, Parker.
And I'm Ray, and we will see you soon.
Bye, guys.